Hi everyone, we are pleased to present our work here at Medcomnet this year. My name is Marco Cominelli, I am a PhD student at the University of Brescia, and today I will be talking about our most recent work on CSI-based localization and about some interesting obfuscation techniques to preserve users' privacy. First, we are going to review the fundamentals of Wi-Fi based localization using neural networks and fingerprinting techniques. Next, we will introduce the first goal of our work. Here we want to understand whether we can increase the overall performance by using location information estimated at multiple nodes. We then present some concepts about obfuscation of the channel state information, and finally we will introduce our second contribution. We want to verify that basic obfuscation techniques are still effective against multi-point attacks. So let's begin with a disclaimer about how we use the term localization in this work. Here we are referring to the ability to localize a person without her knowing. This activity is often deemed illegal, since it definitely violates users' privacy. However, many recent works claim that nowadays this is possible by using, for example, the channel state information embedded in each OFDM frame in Wi-Fi. Let us imagine the following scenario, which might be quite familiar. One person is inside the room together with Wi-Fi devices like access points and stations. An external user that has complete access to some of the nodes will then be able to extract CSI data from each receiving device and use them to locate the unaware victim. One really important thing to keep in mind is that the victim is not carrying any device with her. The CSI conveys some kind of information about the physical environment through which the signal has propagated. If the person moves around in the room, the different reflections of the signal will cause different CSI profiles at the receivers and eventually enable victims' localization. CSI data are very important in an OFDM communication system like Wi-Fi because they allow for accurate equalization of wideband signals. Traditional fingerprinting techniques are able to track one person in a room by studying how the channel response changes as a function of different positions of the victim. An interesting question, which is the one we are going to tackle in this presentation, is whether multiple receivers can actually improve localization. The most evident feature of a CSI is probably its amplitude. In these figures, we plot, like in a sort of a spectrogram, the amplitude of the CSI as a function of time. Even if the patterns are overall quite similar, there are some peculiar differences that depend on the different positions of the victim in the room. We also notice that if the person is not moving, the CSI is not changing between consecutive packets. To exploit this information, we should resort to some supervised learning technique that we can use to identify the complex structures of the CSI. Many recent works have tried to use convolutional neural networks. In these architectures, each CSI extracted from a receiver is fed to the neural network as an array of real and imaginary values. The output of the network is then a choice in a set of predetermined target positions. In our work, however, we mostly focus on the possibility to disrupt unauthorized surveillance attacks that might go undetected. In order to do so, we have introduced in our previous works the concept of CSI randomization, according to which a predistortion should be applied to the CSI to hide position-related information. We will investigate in greater detail which kind of manipulation we can apply, but for now we just state that this manipulation should not degrade the communication performance. We have performed our experiments in the telecommunications lab at the University of Brescia. The lab is approximately a 45 square meter room in which we have identified 8 target points, right in the middle of the room. Then we have positioned 6 Wi-Fi devices around the room, 1 transmitter implemented on a SDR and 5 receivers implemented on commercial off-the-shelf devices, from which we can extract CSI data. Intuitively, measuring the channel response in multiple points should improve the localization performance. However, we first have to decide how to merge the information provided by the different receivers. And to this end, we have identified two possible approaches. The first one is quite intuitive. The final position is decided by majority vote. Obviously, by using this method, sometimes we can run into undecidable points, for example, when all the receivers disagree on the target position of the victim. However, if all the errors are independent, this represents a maximum likelihood estimation. On the other hand, we can feed all the CSI extracted at different nodes for the same received frame to a novel convolutional neural network, specifically trained and tested with this augmented data. This is in principle a very powerful technique, but in this work we will limit ourselves to consider a CNN with a structure very similar to the one we have seen before. We will just skim over the desired properties of the randomization techniques and we redirect interested readers to our paper for more details. In general, the pre-distortion should not alter the power of the transmitted frame and present a channel response that is still likely to be measured in real scenarios. This means that no sudden spikes should be present in the channel response. Moreover, the obfuscation should not be easily reversed nor alter the overall performance of the communication system. As we already said, the main idea is to generate a pre-distortion filter that is applied to the transmitted signal. The pre-distortion filter appears as a random vector or a mask in the frequency domain that modifies the amplitude and the phase of each subcarrier. The filter profile is updated every transmitted packet according to a uniform Markov random process. Here we can see the CSI amplitude extracted by one receiver. On the left, we see that if nothing moves in the room, the CSI amplitude remains unchanged over time. On the right, CSI obfuscation is in place and periodically changes the profile of the CSI. In particular, we can see that the peaks and the zero are in completely different positions. I would like to recall that the pre-distortion is applied at the transmitter side, and that the CSI is extracted by the receivers. Hence, it's not trivial to guarantee that all the points discussed before about how a good CSI randomization should be are satisfied. In order to avoid generating pre-distortion sequences that are too random to resemble real channels, we have decided to include two heuristic solutions in the process. On the one hand, we clip the values of the pre-distortion mask to an allowed range, so that, for example, we cannot multiply some subcarriers by an amplitude factor of 0. On the other hand, we smooth large discontinuities in the pre-distortion mask by applying a moving average on the mask itself. It is very interesting to notice that the order in which we perform this operation has a strong effect on the final properties of the obfuscation. Let us have a look at the graphical representation of this. Here we are plotting the ECDF of the amplification values applied to all the subcarriers using different strategies. In this case, we are first filtering the values of the pre-distortion mask with the moving average filter, and then clipping values below 0.1 or above 1.9. We recall that an amplification value of 1 means that the original amplitude of a subcarrier is not going to be altered. If we swap the filtering and the clipping operations, we get instead this interesting curve. Please notice that the moving average filter works on 5 samples at a time, and since the clipping happens before the smoothing, there are some configuration of the amplification values that happen with probability greater than 0. In fact, the discontinuities in the ECDF correspond to all the possible combinations of clipped values. For completeness, we consider what happens when we do not enforce symmetric clipping. The dashed lines show these results for both the cases considered before, namely if we apply filtering before clipping in blue and if we perform the clipping before the moving average filtering in red. Finally, let us have a look at the results. Here we are showing the classification accuracy over the 8 target positions if we consider each receiver alone. The first line shows that while some positions seem to be better suited for sensing than the localization tasks, all the receivers do fairly well in identifying the correct positions. Please recall that in this scenario, a random guess would be successful 1 in 8 times. It is clear that the pre-distortion reduces the localization performance in all the cases. However, it seems that the filtering before the clipping leads to better randomization in general, and that symmetric clipping outperforms the obfuscation obtained by just clipping the lowest values. Moving to the more interesting case in which we consider multi-point localization, in this table we show the results obtained by using majority voting. In each column, we report results for a different number of receivers, and in each cell we show both the percentage of correct decisions and the percentage of cases in which the receivers could not agree upon a solution. A quick look at the first line of the table is enough to see that the overall accuracy increases with the number of receivers, and that with 5 receivers we achieve 100% accuracy. As expected, when we use only 2 receivers, there will be a larger number of positions that cannot be decided. Again, we observe that the best obfuscation performance are obtained with a symmetric filter and clip. Similar results have been achieved using the data fusion method, for which we have trained other neural networks considering the input of more receivers. Notice that each column refers to a different model, since the dimensionality of the input changes whether we consider one single receiver or an ensemble of 5 receivers. In this case, we could not achieve 100% accuracy with 5 receivers and clean CSI. However, we think that our naive system can be outperformed by better architectures. Our main point here is that the proposed randomization techniques work very well also in this case, with the filter and clip method again outperforming all the other ones. Given that the neural network always gives a single output among the possible choices, there are no cases of undecidedness in this scenario. To introduce our last experiment, we recall that one of the criteria for a good CSI randomization scheme is that the pre-distortion should not alter the communication performance. Here we evaluate what is the impact of different techniques presented before on the packet delivery rate. We have measured this quantity by sending a known number of frames and counting how many of them have been correctly decoded at the 5 receivers. The measurements have been repeated for different modulation encoding schemes, or MCS, which are reported on the x-axis of the graph. In general, higher MCSs achieve higher rates thanks to advanced modulations, but they are also more susceptible to noise and distortion. For each MCS, we are plotting the 90% confidence interval as a vertical bar. First, let's see what the performance are when no distortion is in place. We notice very high PDR and very narrow confidence intervals apart from MCS 9. The PDR never gets to 100%, probably due to the fact that our SDR transmitter does not implement any match procedure. This is the impact on the communication of the methods that provide maximum obfuscation. Even if communication performance is clearly lower, it is not completely destroyed except for very high MCS. This might be due to the fact that the final clipping stage is still introducing some high-frequency components and therefore some systematic error. Indeed, if we consider the other scheme clip and filter, which produces smoother pre-distortion masks, the communication performance improves immediately, and it is virtually undistinguishable from the clean one apart from higher MCS. It is clear that these are preliminary results and there is still a lot of work ahead. However, we will be happy to discuss with you in the live sessions about the theoretical analysis behind these CSI manipulation techniques and about possible future extensions to other localization techniques or security protocols. Meanwhile, I would like to thank you for your attention, and we are looking forward to talk with you at the live session.